Great, thank you. Yeah, so I'll be talking about our work on type systems for security protocols. This is joint work with my collaborators at CMU. So the modern internet landscape relies on a bunch of different security protocols like TLS, QUIC, WireGuard, or more broadly, protocols from the noise framework. But these protocols are generally massive. So for TLS, the defining RFC is around 160 pages, while the OpenSSL implementation of TLS is over 65,000 lines of code, and that's not even counting the code for the underlying crypto. And since these protocols basically run the internet, we'd really like to apply the full power of formal methods and verification to them. So when we look at these protocols, we typically think of them as being constructed in two parts. First, there's a design phase, where we write down the protocol in the abstract and make sure that it's secure. And then we have an implementation phase, where assuming that the design is secure, this is where you do the actual low-level programming. And it's useful to break up the system like this because each phase can be verified separately. This work, OWL, is about the design phase, making sure that the protocol is secure. To ensure that we get secure designs, we aim for computational security, or security in the presence of concrete cryptographic mechanisms over bit strings and against arbitrary probabilistic attackers. This is in contrast to the symbolic model, which axiomatizes the crypto for easier reasoning, but in our work, we focus on the computational model because it's what you ultimately want. Additionally, our work aims for a very high degree of proof automation. This constraint is directly motivated by how big security protocols can be and how tedious manual crypto proofs can be. To show you what I mean about crypto proofs, consider semantic security for a symmetric encryption scheme. Semantic security is typically stated using some kind of security game, like Ink game shown here. The security game basically samples a key K internally, and then allows the computational attacker, A, to input query messages M. And in return, the security game gives the attacker encryptions of M under K. And the encryption scheme here is secure. The attacker cannot tell the difference between this security game and an altered one where you get encryptions of zeros. So while these security games are really convenient for specifying individual crypto systems, applying them to protocols gets tricky. Prior work for partially automated provers in the computational model, like CryptoVerif and Squirrel, at least indirectly work like this. We have a protocol P, and we want to reason about an encryption inside of P. To do so, the tool needs to somehow know about a crypto reduction R, such that P is equal to R, but here R interacts with endgame internally. And once you have a reduction in this form, you can use semantic security to reason about the protocol. So the catch here is that prior work usually does not assume any structure on P itself before you do the reduction, and thus to do the reduction requires a whole program analysis on P. For example, you have to look through all of the code and make sure that it's using the encryption key correctly. Whole program analyses are okay for small protocols, but they don't really scale to large ones. In particular, doing it this way is non-modular. If P and Q are secure separately, you don't automatically get that P running alongside Q is secure. This is really unfortunate because modularity ends up being really important for big protocols. So this brings us to our approach, OWL. So the basic idea of OWL is instead of the tool doing a whole program analysis to find a crypto reduction on an unstructured protocol, we type the protocol using information flow and refinement types to guarantee the existence of a reduction. In turn, our formal soundness guarantee says that if P is well typed, then P is secure, where secure here is a combination of secrecy and integrity goals. The way we achieve soundness here is we do a type systems proof. We prove once and for all that if your protocol is well typed, all of the necessary crypto reductions exist, and therefore the protocol is secure. And once we've done this one-time proof effort, you can reuse it for many different protocols with type checking, which is much easier than a whole security proof. Briefly, the novelty of OWL is that instead of the information flow types keeping track of coarse-grained protocol parties, like Alice and Bob, which is like what you do classically, we have that each cryptographic key corresponds to a fine-grained name, where each name here is treated as a different principal in the security lattice. I'll get back to names in a minute. And using this novel type system, we give each crypto operation a typing rule that succinctly captures its secrecy and integrity guarantees. And what makes our type system usable in practice is that it's actually extendable to a wide variety of primitives, including everything you want for security protocols, like authenticated encryption, digital signatures, public key encryption, and hashing, all that kind of stuff. So I'll now give an example protocol to show you how the type checking works. So say that you have a server and a client who have a pre-shared key PSK. The server then sends the client an ephemeral key, kData, encrypted under PSK, and in return, the client encrypts some secret data X under the ephemeral key. The server can then extract out the value of X using the ephemeral key, kData. So to encode this protocol in OWL, we first begin by declaring the relevant localities, which are basically just the parties. Next, we have name declarations, which determine the relevant cryptographic keys. First, we have that names are annotated with localities, like how X is at locality client. This means that we assume that the client initially has the value of X. Each name here is attached to a name type, which says how the name can be used. Here, X has the name type nonce, which is used for opaque random data, while kData and PSK have this ink key name type, which is used for authenticated encryption. This ink key name type additionally has an associated data type that describes the set of messages that can be encrypted under the key. So here the type associated to kData is name of X, which is a singleton type that only holds the value of this name X, which reflects the protocol. Similarly, the type associated to PSK is name of kData. Annotating the keys in this way, in effect, encodes the invariance that the protocol maintains and assumes. So for example, we have typing rules that say, unless PSK is corrupt, we know that since the encryption scheme is authenticated, any ciphertext that decrypts correctly under PSK contains the key kData. Finally, we have the party code, here for the client, which is slightly modified for readability. The code looks mostly like an ordinary language, except with some small extensions for security protocols. We get an input I, decrypt I under PSK to get K, encrypt X under K to get the ciphertext C, and then output C on the network. And if the initial decryption fails, we just do nothing. The huge advantage of OWL is that because it's defined by a type system, the client's code can be checked completely independently of the servers, in contrast to previous tools where you check the whole protocol all at once. This is a huge advantage because it enables separate verification efforts per party. And as I mentioned earlier, the soundness of our technique relies on information flow checking. Information flow in our system is defined over the labels, given here at the top right. Labels are either atomic labels for names, like X or kData, that's like the bracket, the and of two labels, a special label for the adversary, or a bottom label. The labels for names form a hierarchy, which protects the secrecy of data and avoids key cycles. The hierarchy here, which we derive from these name declarations, states that PSK is on top, with kData below that, and X below that. And since the adversary is given by a label, we get for free that if PSK is corrupt, where corrupt here means less than the adversary label, then by transitivity, anything below it also is. Modeling corruptions in this hierarchical way is central to our security analysis for the type system and automatically rules out certain key compromise attacks. And our tool can handle protocols much more complex than this little example. So here's the hierarchy for our basic example, but in general, OWL can handle key hierarchies looking more like this, where the pre-shared key encrypts not one, but many data keys, each of which encrypts its own data. We handle large protocols like this by borrowing from prior work and using indices, which are basically points where the protocol is parameterized. An example type of index in our type checker are party IDs, which lets you specify families of localities instead of only single ones. So for example, here we have a single server locality, but many clients. In turn, the name X can be parameterized as well. So here we have that X of I is stored at client of I. And I can't go into details, but we specified the pre-shared key, which is at the top, using an existential type, which quantifies over these party IDs. Finally, OWL supports modularity not only within protocols, like separate type checking of parties, but also modularity across protocols using type-based abstraction. Suppose you have a protocol that first does a handshake to establish keys, like kData, and then performs data transfer using those keys, like how we transfer X. Since these are logically two different phases, it would be better to prove them separately. And indeed, you can do this in OWL by having the data transfer and the handshake protocols live in different modules, so that the data transfer module uses the handshake module. Crucially, our type system allows the data transfer module to type check only using the specification of the handshake and not the underlying implementation. This is great because it allows you to instantiate the handshake in any way you want as long as it matches the spec. For example, you can do the handshake with public keys using a PKI, or you can do it with pre-shared keys. So All of this and more can be found in our concrete tool for OWL, implemented as a standalone language and type checker. With a number of case studies, we show that type checking protocols with OWL is competitive with the other two big proof assistants in the space of automated computational proof assistants. Because we perform type checking, protocols in OWL often require much less proof effort than protocols in the other tools. And equally as importantly, OWL enables for the first time separate verification efforts for different parties, subroutines, and subprotocols. Separate verification effort allows you to prototype protocol designs much more incrementally and iteratively than before. Finally, the OWL tool includes a prototype extraction mechanism to Rust, which demonstrates that our protocols are both secure, but also include enough realistic features to obtain concrete implementations. In future work, we're aiming for verified zero-copy implementations. So to wrap up, we present OWL, a new tool for modular automated proofs for security protocols. It's powered by a novel type system using information flow and refinement types. And using this type system, we prove security once and for all. We have a bunch of case studies and a prototype extraction mechanism to Rust. And if you're interested, the project page is linked here. Thank you.
Thank you. Any questions from the audience? Yes.
Thank you, very interesting work. I have one question. Your modular approach seems very nice, but it also seems a bit too nice in the sense that real-world protocols don't have these properties sometimes. So given that your motivation is, say, like TLS, do you have an intuition whether such a protocol could potentially meet the properties that you need to give such a proof, or what's your...
Yeah, that's a great question. So the way that modularity fits together is that you have these like name declarations, and name declarations are essentially invariants over how different parts of the protocol can use the same shared key. So like if you have two different protocols, sub-protocols that use the key in like conflicting kind of contradictory ways, then that's not going to go through the verification process. So these name declarations are kind of the interface.
So maybe let me refine the question. And so for the case studies that you did, could you take those protocols as is, or did you had to already make minor modifications to them to make your proof system work? So basically, how big is the gap between protocols that we think are correct and where you can prove that they are correct using your system?
I see. Yeah, well, so for the small case studies that we did, which are the classic like toy version of Kerberos and that kind of thing, we didn't have to do any modifications, but we expect that when we go to like WireGuard and TLS and bigger ones, that there will be more nuanced issues to find out.
Oh, thank you very much.
Matteo.
Hi, nice talk. I was curious, so you talk about the verification of security protocols. Which security properties do you actually verify with your type system?
Yeah, that's a good question. So our type system basically has a secrecy component, which is basically a computational form of non-interference, if you know what that is. And we have an integrity component as well. Because we have refinement types, and the integrity guarantees essentially any piece of data you have has the corresponding refinement. So using these secrecy and integrity properties is how you specify security.
Okay, thank you very much. For another question, how does this type system compare with the F-star, which has also been used to verify compositional cryptography protocols with computational guarantees?
Yeah, that's a good question. So the big deal here, though, is that our type system is very modular and abstract in a way that the F-star verification effort is more deeply intertwined with the implementation and the specification of the protocol. So that's one big thing. Another thing is we have like kind of modular type-based abstractions of what the encryption does, while the F-star work models the encryptions in a much more low-level way, closer to the actual cryptographic security assumption, and that basically encourages a much higher proof effort.
Thank you. So we are running out of time, so we will take any additional questions offline. So we move on to our next speaker. Let's thank Joshua again.